we are going to be talking about today is an in-depth look at the concept of sinusoids. And then once we complete that, we are going to look at circuit analysis, where there are sinusoidal excitation signals in place. So let's start with our sinusoid review. And I am notoriously bad at not noticing when something pops up in the chat. So by all means, yell at me and be like, hey, somebody said something, and then I will answer their question, etc. So let's first look at what a sinusoidal signal looks like. Okay. So I'm going to attempt to draw a sinusoidal signal. Where let's call the positive axis or the y-axis, let's just say for the sake of argument that it is some voltage waveform, and the horizontal axis then represents time as it progresses. So a sinusoidal signal is going to look something like this. Where the mathematical representation of this voltage, V of t, is given by Vm cosine omega t plus some phase angle theta v. And I'm going to talk about what all these constituent parts in the math equation look like on our graph. Okay. So the quantity Vm is our magnitude. So that's the maximum value we have. It's also measured from the horizontal axis, and it also corresponds to the minimum value. Okay, so Vm is the magnitude or amplitude of the sinusoid. Omega is the angular frequency of the sinusoid. So we're going to develop some relationships here because you can't really see omega in the graph. All right. So let's say that this length from the negative peak to the next negative peak is the period of our sinusoid given by capital T. Where the period is simply the amount of time it takes to go through one cycle of this periodic signal. Okay. The linear frequency, F, is equal to the inverse of the period. So effectively, the period says it takes some number of seconds to complete one cycle. The linear frequency says you complete some number of cycles per second. Angular frequency is related to linear frequency by the following relationship. Omega is equal to 2 pi f, which effectively means that the sinusoid goes through a full circle of 2 pi radians every cycle. And we can relate it directly to our period then as simply 2 pi divided by capital T. Okay. The next bit that we need to look at is the phase angle, theta v. Okay. So theta v is the phase angle which represents, or I get a better way to put this, which determines the function's value at t is equal to 0. So what I mean by that is if we had the function cosine, let's say that we had, let me do this red. That's just a quick aside here. If we had the function y of x is equal to 6 cosine 4x, what would y of 0 be?
Six.
Right. So a phase angle of 0 means that we don't have to fix anything, okay? Now, if we had z of x is equal to 6 cosine 4x plus 13 degrees, z at 0 is simply 6 cosine 13 degrees. So that phase angle tells us effectively where our function starts from. Another way to think about it is it represents how much we have shifted our sinusoid along the horizontal axis, okay? So let me explain what I mean by that, all right? So if we look at this terribly drawn sinusoidal waveform, V of t up at the top in blue, this could represent a cosine function that has been shifted to the right by some amount of time, okay? I say that because we would expect a cosine function with 0 phase angle to have its maximum amplitude at t is equal to 0, which whoever answered my question a moment ago effectively figured out, okay? Since the maximum value occurs at a later point in time, that means that this is a cosine function with a negative phase angle, because a shift to the right corresponds to a negative phase angle, okay? And I'll explain that mathematically in just a moment. We could also express this particular waveform as a sine function that has been shifted to the left. By a small amount. And I say that because if it were a sine function, we would expect it, the value of the function to be 0 at t is equal to 0, but we see instead that its value is 0 at some time slightly before 0, okay? So that phase angle, this guy right here, literally just represents, to some extent, how much we've slid this graph in the horizontal direction. So if we slide it to the right, we're having negative phase angles. If we're sliding it to the left, we're introducing positive phase angles. That may seem counterintuitive, but it's all about the way that we read the graph, okay? And so what I mean by that is if time, at this point right here, the origin is t is equal to 0, then all of the points to the right are later in time than t is equal to 0. And so we need to introduce a delay to get there, which is where a negative phase angle comes from. All of the points to the left of the origin occurred earlier in time than t is equal to 0. So we have to put an advance in to make up that difference, which is why shifts to the left introduce a positive phase angle. So let me write all this stuff down. Positive theta v causes the signal to be shifted to the left by delta t is equal to theta v divided by omega. The negative phase angles causes the signal to be shifted to the right by delta t is equal to theta v divided by omega. Now, omega, the angular frequency, is measured in radians per second, but phase angles are traditionally measured in degrees. So if you're ever trying to calculate the instantaneous value of a voltage waveform or something like that, you need to be careful regarding the units of your angle, because inside that cosine function is an angular frequency that's being multiplied by time, giving you an angle in radians, to which you are adding a phase angle, which is measured in degrees. So the conversion between degrees and radians is this relationship. There are 180 degrees for every pi radians. So if you want to convert radians to degrees, you multiply by 180 over pi. If you want to convert degrees to radians, you divide by 180 over pi. All right. So anybody have any questions on, I guess, the parts that make up a sinusoid? All right. So the next thing that I want to do here is then introduce a series of trig identities that we will utilize. Why is this being difficult? I 100% do not expect you all to memorize these. In fact, we're probably only going to use a few of them, but I'm going to give you pretty much all of them that could wind up being used, okay? So our first trig identity is scroll down to my list here so I don't make a mistake, is that cosine omega t is equal to sine omega t minus 90 degrees. So this trig identity lets us convert a cosine function into a sine function. So what I mean by that is if we had 3 cosine 4t plus 11 degrees, this would be the same as 3 sine 4t plus 111 degrees. Okay. Our second trig identity, which is going to be sine of omega t. Oh, sorry, this should be plus 90 degrees. My apologies. Our second trig identity is sine omega t is equal to cosine omega t minus 90 degrees. So if we had 8 sine 13 pi t plus 60 degrees, this is identical to 8 cosine 13 pi t
Dr. Hartman,
minus 30 degrees. Yes, ma'am.
for the first example, should that be 101, not 111?
Yeah, I probably added in my head incorrectly.
Okay.
Yeah, no,
Okay.
simple addition. Nope, you're 100% right. 101 degrees. Thank you. I think McKinley and Shaw for saying something. Yes. So the intention there was to just add 90 degrees, not do math incorrectly. I apologize for that. I shouldn't need to use a calculator for simple addition, but apparently I need to. All right. Our third trig identity is negative cosine omega t is equal to cosine omega t plus or minus 180 degrees. It literally doesn't matter if we add 180 or subtract 180, that gets us to the exact same point on our circle effectively. So really just pick one and go with it and you'll be okay. Okay, so we get rid of a negative sign by shifting by exactly 180 degrees. And we'll see the exact same relationship to get rid of the negative sign in front of a sine function. So these first 4 identities we are going to use extensively in a couple of minutes when we talk about comparing sinusoidal signals. Okay, so I want to put a mark by the 2 that I actually expect you to quote unquote learn in this class. All right. We need to know how to convert a sine function to a cosine function in order to do our frequency domain circuit analysis correctly. So we absolutely need to learn trig identity number 2. And we need to know how to convert a negative or a cosine function with a negative magnitude into a cosine function with a positive magnitude, which means we desperately need to know trig identity number 3. We are pretty much never going to convert a cosine function to a sine function in our circuit analysis. And if we're able to convert sine functions to cosine functions, then trig identity number 4 is redundant. Okay. So these are the easy ones, let's say. And I'm running out of room, so I'm going to go to the next page if that's okay. Let me check the chat. Relatable. Okay. All right. So our next 4 trig identities are going to be for mathematically manipulating functions. And we are going to use some of these today. And my goal is to show you a shortcut to where learning all of these will effectively be obsolete. That's my goal for today. Okay. But it is important that I at least introduce them. So our first of these more difficult trig identities is sine alpha plus beta is equal to the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Okay. So this trig identity and the next several that we introduce will help us kind of deconstruct and reconstruct sinusoidal signals into easier parts to digest and play around with. Okay. Trig identity number 6 is cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. That is not a mistake on that minus sign in the middle there. Then we will have sine alpha minus beta, which gives us sine alpha cosine beta minus cosine alpha sine beta. And our last one of these is cosine alpha minus beta, which is cosine alpha cosine beta plus sine alpha sine beta. Okay. Again, I do not expect you guys to actually memorize literally any of these 4, but at least for today and maybe the next lecture or 2, until we've really nailed down the shortcut, we might have to come back to looking at these. Okay. This next identity is a very, very important identity that we are going to utilize later on in today's lecture. It's what's called Euler's identity. And Euler's identity says that the cosine of an angle, let's call it theta, plus j times the sine of that same angle is equal to e to the j theta. This is Euler's identity. This is nothing more than the conversion between a rectangular coordinate complex number and a polar form coordinate complex number. So we actually effectively covered Euler's identity in our last class meeting. We just didn't do it explicitly like this. And then another trig identity that we're going to wind up using extensively in this class is cosine angle 1 times cosine angle 2 is equal to 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. There are actually three other identities that we could list out here, but because we know how to convert any sine to a cosine, we can always actually just rely on this guy, number 10, whenever we're multiplying sinusoids. Okay. So these are our trig identities that we're going to be toying around with here a lot in our sinusoidal steady state portion of the class. So I just wanted to kind of give them all to you in one go, and then I'll remind you of them when we actually apply them as well. Any questions regarding these identities? All right. So I want to now talk about the rules for comparing sinusoids. So our first rule is that all signals must be expressed as either sine or cosine functions. So what I mean by that is that if we had a signal, let's call it V1 of t was 6 cosine 13t plus 14 degrees, and another signal V2 was 11 cosine, sine 13t plus 50 degrees. These are both voltage signals, so they should both have units of volts. We can't perform this comparison without converting the sine function to a cosine or our cosine function to a sine. So everything has to be expressed as exclusively sine functions or exclusively cosine functions. And electrical engineers typically work exclusively in cosine functions. So we would apply trig identity number 2 here, and we would have 11 cosine 13t minus 40 degrees volts. And we could then perform whatever comparison we do. Rule number 2 is that all signals must be expressed with positive magnitudes. So this is where we would apply trig identities 3 and 4 from the list. So for example, if we had V3 is equal to -4 cosine 13t plus 8 degrees, we could write this as +4 cosine 13t minus 172 degrees, or positive 188 degrees. It wouldn't matter particularly which one we did. Our third and final rule is that all signals must have the same frequency. So in all of these waveforms that I've described here, V1, V2, and V3, all of them have the same angular frequency of 13 radians per second. There is no trig identity to correct for signals that have different frequencies. We just cannot do that comparison at all. Okay. So what I want to talk about now is the comparisons that we are going to be doing as electrical engineers, which is usually just simply determining whether one particular signal leads or lags the other one. Okay. So let me try to explain the concept of leading and lagging here using these three signals. And I'm going to apologize in advance because I know that this particular drawing is going to be pretty crappy. So let's say that we have a dot like so, where our y-axis is measuring voltage and our horizontal axis is measuring time. Okay. So my signal V1, actually, let me make this slightly easier on myself. I'm going to call this omega t so that I can say that this is 90 degrees, 180 degrees, 270 degrees, 360 degrees, etc. And I could do the same thing on the other side, negative 90, negative 180, etc. Okay. So signal V1 has a positive phase angle of 14 degrees. So that means that its peak amplitude is, let's see, 6 is going to be something around here. Let's call 11 to be something up here. And 4 would be something like this. Okay. So its peak value is going to be at 14 degrees, shifted to the, and we're going to have a shift to the left. So something like this. All right, so that's what V1 is going to look like. V2 has an amplitude of 11 and negative 40. So its positive peak is going to be something like around here. So let me just try to draw this as least crappily as possible. Something like this. And then finally, my green guy, V3, negative 172. So that shifted way over here. Something like this. Now, again, I struggle to draw sinusoids or whatever. So I promise we're going to figure out what this hot garbage is that I've drawn in a slightly easier fashion in just a minute. Okay. But I want to explain what the concept of leading or lagging is for these actual sinusoidal representations, because we're going to be doing labs where we're asked to determine which signal is leading the other. Okay. So leading means that the signal hits its peak earlier in time than what we are comparing to. So what I mean by that is if we're looking at the positive peaks of the red curve and the positive peaks of the blue curve, we can say that the red curve leads the blue curve because it hits its peak earlier in time. Similarly, if we were looking at the blue curve and the green curve, where their positive peaks are closest, so this point and this point, we could say that the blue curve is leading the green curve. Is everybody okay with that?
Yes.
Yes, sir.
I know it seems simple, but it's so dang easy to make a mistake with these, okay? Lagging means that the signal hits its peak later in time. Than what we're comparing it to. So that means we could say that the green curve lags the blue curve. We could say that the blue curve lags the red curve, etc. So if it hits its peak later on, it's lagging. If it hits the peak earlier than what we were comparing it to, it's leading. Okay. So just as a quick aside here, if we're looking at these positive peaks, I'm going to call this guy 1, 2, and 3. We can see that V1 leads V2, or alternatively, we could say that V2 lags V1, and similarly, we could say that V2 leads V3, which is the same as saying V3 lags V2. Now, it is often useful for us to know exactly by how much one signal leads or lags another one. And it's very hard to do that measurement using this type of graph. So what I'm going to introduce to you guys is what's called a phase graph. Okay. So what a phase graph is really just a snapshot of all of the signals at a particular instant in time. And typically that instant in time is t is equal to 0, so that all of the cosine bit goes away and we just have the phase angle part left. So a phase diagram of our three signals would look something like this, where this axis is 0 degrees, up here is 90, over here is plus or minus 180, and down here is negative 90. So our first signal was V1 is 6 with an angle of 14 degrees. Oops, slightly too far. So that would look something like this. Let's call this V1, where this angle right here is 14 degrees. Our waveform V2 had an angle of negative 40 degrees. So that means V2 would be something like this. So it's longer in magnitude, but it has a phase angle of negative 40. And then finally, if we looked at the green curve, we have a phase angle of negative 172 degrees. So that guy would look like, oops, keeps going slightly too far. This, where the angle measured from the horizontal axis is negative 172 degrees. So this guy is V3. Okay. So this is what our phase diagram would look like. Now this is a bit cluttered, so I'm going to redraw things over here to the right, and we can actually do a comparison so that I can explain how that works.
When picking the peaks to compare lagging and leading, do you have to pick them between negative 180 and positive 180?
It doesn't particularly matter,
Okay.
right? So if I did 188 degrees, that's the exact same thing as positive 188 degrees is the exact same thing as negative 172 degrees. So it's still going to be the exact same place on the graph. It's just we're measuring the angle in the opposite direction. Does that make sense?
What I'm saying is, if you look at the first graph of the loops and stuff, if I pick the right top loop of the red one, would that now be the lagging strand?
So if you're saying you picked this point way over here.
Yes, sir.
So that would be an angle of 374 degrees, which is still going to show up at the exact same spot on our phase diagram.
Okay, right.
Right, because it's just one cycle later. Actually, actually, that's not that's not technically correct. It would be an angle of negative 346 degrees, but it's still the exact same spot on the phase diagram, because between this point and this point is exactly 360 degrees. When we're measuring how this progresses as the angle changes.
So you're looking more at the phase diagram, or which one leads and lags more than the graph up top?
Yes.
Okay, thank you.
Yeah, no problem at all. Yeah, so the top diagram, there's nothing particularly wrong with it. Like you can tell leading and lagging by, you effectively just pick the two peaks that are closest together, and then whichever one comes first is leading, and whichever one comes second is lagging. But to me, the phase diagram representation, which is what we're trying to go through right now, actually contains a lot more information, and it's, to me, much easier to interpret. So let's look at just the signals V1 and V2 real quick here. Okay. So again, V1, something like this. Our angle here being positive 14 degrees. V2, my stylus will write something like this. our angle being negative 40 degrees, okay? So if I want to know by how much, let me do this over here, running out of room. By what angle does V2 lag V1? What I do, I'm gonna extend this just real quick. So what I do is I start measuring from V1, and I'm gonna measure in this direction for lagging, and this direction for leading, okay? So effectively, lagging is clockwise because as the angle gets more and more negative, we're looking for something that's occurring later and later in time with respect to our reference. Leading is measured counterclockwise because as the angle gets more and more positive, we're looking for something that is occurring earlier in time with respect to our reference. So if we're looking for lagging, by how much V2 lags V1, we start our measurement at V1 and then just add up the angles until we hit V2, which in this case would be 14 degrees and 40 degrees or 54 degrees. If we wanted to know by what angle V2 leads V1, we'd have this guy right here, which is 90 minus 14 degrees. Then we'd have this 180 degrees. And then this guy right here, which is 90 minus 40 degrees. So that would be, I'm going to use a calculator, so I'll screw this up. 180 plus 90 minus 14 plus 90 minus 40 is 306 degrees, or 360 minus the 54 degrees that we found earlier. Okay, so just to be super clear here, let's do another example using completely new numbers. I'm going to draw a phase diagram. By the way, the magnitudes actually don't even remotely matter on a phase diagram. Somebody give me a phase angle. Let's call V, let's do it in red and blue again.
105 degrees.
Okay, so angle of V1 is positive 105 degrees. And somebody give me a phase angle for our voltage V2.
$24.
Positive 24, negative 24.
Negative.
Negative 24. Okay. So on our phase diagram, then V1 would be somewhere over here, where this angle is 105 degrees. V2 would be somewhere over here, where this angle is negative 24 degrees. I want to know how much V1 lags V2. Okay. So V2 is my reference here, all right? Because we're comparing what V1 is doing to V2. So whichever one is second effectively in the sentence is our reference. So we're going to start here. And since we're measuring lagging, we're going to go in this direction. So the answer would be, let me do it in, I guess, this color. This angle, 90 minus 24 degrees should be 66. Is that right? then I have 90 degrees here. Then I have this guy, which is 180 minus 105, or 75 degrees. And I would just add those three together. So let me just make sure 90 minus 24 is that, so I don't make another mistake. Yeah, 66. So 66 plus 90 plus 75 is 231 degrees. Everybody okay with this leading and lagging measurement stuff? I'm asking because I know for a fact you've got multiple homework problems on it.
How did you get the initial V1 and V2 values, the 105 and the negative 24?
I asked students to just give me random numbers.
Okay, I just wanted to make sure. Thank you.
Yeah, those were just completely pulled out of thin air, and then we did the comparison. So to reiterate, whichever quantity is the second one, so if we want to know by how much V1 lags V2, we start measuring from V2. Lagging is clockwise, leading is counterclockwise. Okay. Now I want to give you guys a word of warning regarding your web work problems on this stuff. Okay. Web work literally cannot tell the difference between 15 degrees and 375 degrees or negative 345 degrees. Okay. So even though they are all equivalent angles, web work can't tell the difference between them. So if you use the steps that I've detailed here on your homework problems, and web work is telling you that you got the wrong answer, all you need to do is add 360 degrees to your result, check that, and if web work doesn't like it, subtract 360 degrees from the result you got. Web work will like either what you got originally plus 360 or minus 360, absolutely guaranteed. I know that that's tedious and annoying, but it's just the way that web work interprets things. It only looks at numbers. It doesn't understand, I guess, what the concept of an angle is or equivalent angles. Is that clear?
Yes, sir. Thank you.
All right, so just trying to save you guys headache.
Dr. Hartman,
Yes.
why is the 66 positive and not negative?
So that's a really good question. So we're just measuring positive from wherever we started from. Okay, so the expectation here is that we're always going to wind up getting a positive answer regardless of which direction we go. So I'm saying it's positive 66 because it takes 66 more degrees for me to hit negative 90. Then there's positive 90 because there's a 90-degree difference between negative 90 and negative 180, etc.
Okay.
Does that make sense?
Yeah.
Yeah, so you should get a positive angle no matter which way you measure. Or
Dr.
leading-
Hartman,
Yes, ma'am.
do you mind doing the leading for the one we just did too?
So let me ask you a question then. Is that McKinley?
Yes.
All right, so you tell me what we're going to do. So I'm just going to literally write down and then we'll do whatever it is. So how much V1 lags V2, or excuse me, V1 leads V2 or V2 leads
Sure.
V1?
V1 leads V2.
All right, so V1 leads V2. And I'm going to erase this other stuff.
Okay.
So V2 is still, what the hell just happened? Sorry. V2 is still our reference point, but now we're going to measure in the opposite direction. So this is just going to be 24 plus 105.
Plus 105. Okay. Yeah. Thank you.
Yep, 129 degrees. No, not a problem at all. I'm happy to answer questions on this stuff because it seems so easy, but legitimately can be a rather confusing topic. Like I constantly have to be like, oh wait, which way is which? So it doesn't hurt my feelings to answer questions because I know if it confuses me and I'm a jackass that has a PhD in this stuff, It's definitely going to confuse some of you guys, so I'm happy to explain it. Any other questions on this? All right, so now that we have what I believe to be a reasonably good grasp on the concept of sinusoids, let's make life difficult and start analyzing circuits involving sinusoidal excitation, okay? So I'm going to call this forced response due to sinusoidal excitations. We're going to talk our way through this for a minute. I'm sorry if you guys hear like a low grunt in the background. My dog is snoring like crazy. So if we have the following circuit, and let's just talk about something very generic here, okay? We have a voltage source connected to, let's say, some resistor in series with some inductance L. And we want to know what this current I is. If Vs is a DC source, we should expect that our current I is a DC current. Does that make sense?
Yes, sir.
Yes, for all of our DC circuits where we didn't have switches, perturbing anything, we got DC responses, okay? So the response of all of the circuit, and so by that I mean literally every voltage and every current is established by the form of the excitation signal. So if I look at a circuit where I have some source voltage Vs of t, so a time varying voltage, and then I look at that same resistor and inductor, R and L, and I now call this response I of t. If my voltage source Vs of t is of the form Vm cosine omega t plus theta v, then it does not seem unreasonable to me that my current will be of the form Im cosine omega t plus theta I. So effectively, what I'm trying to impress upon you here is that if we excite a circuit with a sinusoidal signal, we should expect that our response, all of our voltages and currents across all of our elements, will also be sinusoidal in nature. Does anybody have a problem with that? All right, nobody's saying anything, so we are going to analyze a circuit. So the circuit that I want to look at is this guy. I have a sinusoidal voltage source. I'm going to tell you what its value is in a moment. I have an 8 ohm resistor. And I have a 50 millifarad capacitor. What I want to determine is the current IS of T leaving the voltage source. And I am going to say that my excitation voltage, Vs of T, is 12 cosine 5T plus 10 degrees volts. Okay. So what we are going to do first here is rely on our current knowledge of how resistors and capacitors and all that kind of stuff behave to solve this problem in the time domain. Okay. So somebody tell me how you think we might be able to go about solving a problem like this.
Would you solve for the current for the resistor and then the capacitor and add together?
That is a stellar idea. So I believe that was Carter. His suggestion, I'm sorry if I'm attributing it to the wrong person, is that if we can figure out this current IR of T, and we can figure out this current IS of T, Kirchhoff's current law tells us that, or excuse me, that should be IC of T, my apologies, that IS of T is just IR of T plus IC of T added together. So I'm going to go ahead and I'm going to write that down. So IS of T is equal IR of T plus IC of T. Are we all okay with this application of Kirchhoff's current law?
Yes.
To me, fairly straightforward. Don't hear anybody in opposition. So let's break this down. What do you guys think the current flowing through the resistor will be? Just based on our knowledge of how circuits work to this point.
Vs of T over 8.
Exactly right. Vs of T over 8 ohms. So 12 divided by 8 is 1.5. And so we should have 1.5 cosine 5T plus 10 degrees volts, or excuse me, amps now, my apologies, for our resistor current. IC of T. So we know that the current that flows through a capacitor is the capacitor value times the derivative of the voltage across the capacitor. Since the voltage across the capacitor in this case is just our source voltage Vs of T, we can say that IC is C dVs by dt. Anybody fundamentally have a problem with that? Nobody's saying that they don't like it. So let's go ahead and do some math here, right? So 50 millifarads, that's 50 times 10 to the minus 3. A farad is an amp second per volt. How do we take the derivative of 12 cosine 5T plus 10 degrees?
Chain rule?
So chain rule is definitely going to be involved. I think somebody was saying something and then got cut off.
Negative 60 sine 5T plus 10 degrees.
Yeah, so 100% you're correct. We're going to walk through it in steps here, right? Just so that we're clear with everybody. So generally speaking, the derivative of cosine omega t plus theta v, or just some phase angle, is going to be negative omega sine omega t plus that same phase angle. So I'm going to take my 12 volts out. Omega is 5 per second because radians is a dimensionless quantity. And then I'm going to have negative sine 5t plus 10 degrees. And if I multiply all these constants out, what I get is negative 3 sine 5t plus 10 degrees amps. And from this, IS of t is equal to 1.5 cosine 5t plus 10 degrees minus 3 sine 5t plus 10 degrees amps. Does anybody have a problem with this?
Quick question. Where did the 12 volts and the 5 seconds to the -1 come from?
So the 12 comes from this guy and the 5 comes from here.
Thank you.
All right, so here's the question that I want to ask you guys right now. We have an answer, this guy right here. Why doesn't it look like this?
We took a derivative.
So,
In terms of just cosine.
okay, so that's one thing. That's a fantastic thing, okay? So, let's put everything in terms of cosine and see what happens. So that would be 1.5 cosine 5t plus 10 degrees minus 3 cosine 5t minus 80 degrees amps. Can we just directly add those two cosine functions together? I would argue the answer is no, because they have different phase angles. I want to pull up a website here real quick. Please let me know if you can see it.
Yeah, we can see it.
Okay, so I'm just going to turn off these two real quick, if it will let me. It's being difficult. All right, so this Y1 curve represents the current flowing through our resistor, where I had to use a conversion factor of pi over 180 degrees because Desmos defaults to angles and radians, okay? So that seems fairly straightforward. This guy right here is the current flowing through my capacitor, also a simple sinusoid. If I look at both of them together, it looks a bit wonky, but I have down here at the bottom the result of adding those two signals together, and it makes a single sinusoidal signal, right? So if I add one sinusoid having an angular frequency of 5 radians per second to another sinusoid having an angular frequency of 5 radians per second, I should be able to get my answer as a single sinusoid having an angular frequency of 5 radians per second, because that's exactly what this graph looks like. So what I'm going to do now is walk you through the math that entails, okay? So let's start with, actually we can use this representation here. I'm going to put a box around it because it's kind of special and we're going to revisit it in a moment. So I'm going to put a box around this result. So what we're going to do for the next several minutes is use some of the trig identities that we talked about earlier. Okay. So in particular, I believe we're going to use trig identity number 6 twice, it looks like. Okay. So I have, go away thing, 1.5 times the cosine of 5t, which is an angle, plus 10 degrees, which is an angle. So I can use trig identity number 6 to split cosine 5t plus 10 degrees into cosine of 5t times the cosine of 10 degrees minus sine 5t sine of 10 degrees. Then I have minus 3, and I can use that exact same trig identity. Actually, I need to use the different trig identity because I have it's cosine alpha minus beta in this case. So that's going to be trig identity. This one was trig identity 6. This next one is going to be trig identity 8, I believe. So this is going to look like cosine 5t cosine 80 degrees plus sine of 5t sine of 80 degrees. Is everybody okay with the application of identity 6 to get here and identity 8 to get here?
So you use the positive 80 and not negative 80, even though it's minus?
So let's go back to and look at our trig identities real quick, because that's a fantastic question. Scroll, scroll, scroll. Sorry, slightly too far. So trig identity 6 says when I have cosine alpha plus beta, I use this guy. And trig identity number 8 is whenever I have alpha minus beta, where beta in this case would be positive 80 degrees. Does that clear that up?
Yeah.
Okay. I could have just used trig identity 6 twice with beta being a negative angle, and I'd literally get the same result. So it doesn't particularly matter as long as I'm using the right identities there. Okay. So cosine of 10 degrees, sine of 10 degrees, cosine of 80 degrees, and sine of 80 degrees are literally just numbers, right? So what I mean by that is I'm going to rearrange this slightly. So I'm going to say that this is 1.5 cosine 10 degrees times the cosine of 5t minus 1.5 sine of 10 degrees sine of 5t minus 3 cosine 80 degrees cosine 5t, and negative 3 times positive is going to be negative 3 sine 80 degrees sine 5t. Is everybody okay with the distributing the constant terms out front and the slight amount of rearrangement that I've done here? Yes. All right, so I can do 1.5 times cosine of 10 degrees in my calculator, right? So 1.5 cosine of 10 I'm going to store this as variable X. And I'm going to do this in blue. So I'm just going to say X here is equal to 1.477, where this bit is what I'm calling X. And I'm going to call this bit Y, where that's just negative 1.5 times the sine of 10 degrees. And that is negative 0.260. I'm going to call this bit Z. So negative 3 times the cosine of 80 looks like negative 0.521. And I'm going to call this bit T. I'm labeling these because that's the variables that my calculator can handle. So negative 3, sorry. Negative 3 sine 80 degrees is negative 2.954. And now what I'm going to do is just going to group my terms together, right? So my cosine terms is going to look like X plus Z. And my sine terms are just going to look like Y plus T. And so if I do that, let's see, X plus Z looks like 0.956 cosine 5t, and then Y.
Should you subtract the 0.521 or the negative 0.521?
So let me scroll up here and answer that question. Okay. So when I did those calculations, I lumped the negative sign in with the coefficient. So negative
okay.
1.5 sine 10 degrees gives me the negative 0.260, etc. And so I'm going to also have negative 3.215 sine 5t. I'm going to put a different color box around this guy because we're going to revisit it in a few minutes. But unfortunately, we are not done. Okay. So just as a refresher, our ultimate goal here is to get a signal of this form where we have a magnitude, a single cosine function, and a phase angle. Okay. We have taken our the sum of two sinusoidal functions in the form that we want, and we have gotten it to the sum of sinusoidal functions that have no phase angle. So we've done something, okay? We're effectively now going to use a couple of trig identities to get back, okay? So what I mean by that is, let's look at just this part right here and this part right here and look at trig identity number 6 again, okay? So trig identity number 6 says IS of t, which is, let's just generically put this, A cosine alpha plus beta is equal to A cosine alpha cosine beta minus A sine alpha sine beta. I've simply adjusted that trig identity number 6 I gave you guys earlier and we applied a few minutes ago to include multiplying by a common factor of A. Everybody okay with that? So if beta is equal to 5t, this 0.956 represents A cosine alpha. And this 3.215 represents A sine alpha. So,
Dr. Hartman,
yes,
it's the positive 3.215, not including the negative because of the formula.
yes, that's correct.
Okay. Okay.
So, all right, so sorry, let me collect myself here. All right, so let's figure some stuff out, right? We have two unknown quantities, A, our magnitude of our resultant thing, and alpha, which is going to be the phase angle of our resultant thing. Okay, so if I have A cosine alpha and I square it, and I have A sine alpha and I square it, this is going to look like A squared times cosine squared alpha plus sine squared alpha, which is just A squared. Everybody okay with that? Where this guy is just 1. So if we're okay with applying that identity, cosine squared plus sine squared is equal to 1, then that means that our magnitude A is the square root of 0.956 squared plus 3.215 squared. Or where do I have this written down? Sorry. 3.354 effectively amps. So that's our amplitude. Our phase angle, sorry, this should be theta I in this case. Well, actually, sorry, because we're calling it alpha, so I should be consistent here, is going to be the inverse tangent of negative 3.215 over 0.956, which is positive 73.435 degrees. And from this, IS of t is 3.354 cosine 5t plus 73.435 degrees amps. I'm going to put a green box around this. Now, let me ask you guys an honest question. How awful was that?
I have no words.
Yeah, it's pretty terrible. If that was the level of math that was involved in analyzing all sinusoidal circuits, and recall, this is just a voltage source in parallel with two elements. I feel very strongly that no one would use AC power because it would be practically impossible to design for. Okay. So keep these numbers in mind. All right. What I'm going to ask you to do, I'm going to scroll up here. And I'm going to look at this bit right here. I'm actually going to take it, move it to the next page so we can look at everything at the same time. Okay. Make a copy of this, edit, copy. Go to the next page, and let's just drop it down here. So this is going to be one of those shortcut things. Okay. So Euler's identity says that this guy right here is the real part of 1.5 e to the j 5t plus 10 degrees. And Euler's identity says that this guy right here is the real part of 3 e to the j 5t minus 80 degrees. So what I would like you guys to do is get your calculators out, if you don't mind, and do the following complex operation. 1.5 angle 10 degrees minus 3 angle negative 80 degrees. And tell me what you get as both a polar form complex number. I would prefer that one first, and then a rectangular form complex number.
3.354 with an angle of 73.434 or 435.
3.354 with an angle of 73 point what?
435.
435 degrees. All right. So it is not remotely a coincidence that we get the exact same magnitude and phase angle from doing that complex operation as we get doing all of that terrifying calculus and trig identities. So we spent roughly 25 to 30 minutes earlier to get this guy. And we just found out that if we just look at those time domain signals as complex numbers and add them together, we get literally the exact same result. So that's pretty interesting. And we're going to talk about why that works in just a moment. What is the rectangular representation? Euler is absolutely a boss. It is a shame he died pretty much penniless in Russia about, I think 70 years ago.
That's tragic.
The rectangular is 0.956 for the real part and 3.214 imaginary.
All right, so let's look at this guy right here and compare it to this. It's the exact same numbers, except that the sign on the sign part is flipped. Also, not remotely a coincidence, okay? I'm pointing this out because there are going to be several homework problems where you are asked to do manipulation of sinusoidal signals. And what I am trying to impart upon you is that you should never do what we wasted 25 minutes doing. You should convert your time domain signals into what's called the frequency domain by expressing them as a complex number. And then you can use simple complex math, just like addition and subtraction, to avoid doing tons and tons of trig identities. Okay, so complex math is a wonderful, wonderful thing. All right, so let's talk about why this works. If I have a generic black box network, okay, so I don't care if it's resistors, capacitors, inductors, or some combination thereof. If I have a black box network, and I input a signal, which I'm going to call x1 of t, where x1 of t is a voltage, Vm cosine omega t plus theta v volts, and I measure a response that I'm going to call an output y1 of t. We just showed that we should get a current waveform, Im cosine omega t plus theta I. And actually, we could take a moment here to throw our numerical result into Desmos and prove that it is that exact same single sinusoidal function that we were looking for. Okay. But anyway, okay, so if I input a sinusoidal voltage, my output is a sinusoidal current. Everybody okay with that? We literally just spent a ton of time proving it. Let's take that same black box network. But this time, instead of putting in a cosine function as our input, let's put a sine function in as our input. So let's call this x2 of t, and we're going to measure an output y2 of t. So if x2 of t is Vm sine omega t plus theta v, what do you think a reasonable guess at what our output signal should be is?
Im sine omega t plus theta I.
Exactly right. If we put a cosine function in, we should expect to get a cosine function out. If we put a sine function in, we should get a sine function out. That shouldn't be particularly tricky because we know that sine functions and cosine functions are literally the same thing, just shifted by 90 degrees. So that's not a problem there. So how many of you remember something about the scaling or homogeneity property of linearity? All right, I'm getting crickets. So the homogeneity property of linearity states that if you scale the input by a non-time varying amount, the output scales by that same amount. So if we have a system and we apply a voltage of 2 volts and see that the current at the output is 1 amp, if we apply a voltage of 4 volts, we should expect the current at the output to increase to 2 amps. So we scaled the input by a factor of 2, we scaled the output by a factor of 2. We did lots and lots of problems working that stuff out when we were talking about the concepts of superposition and linearity. Okay. So what I'm going to do here is I'm going to scale my input x1, or excuse me, x2 by a factor of j, because j is not a j is a time invariant quantity, right? It doesn't change with time. And so that means that my output should scale by a factor of j as well. So if I put a j here, my output goes up by j here. Now, if we take that same network but this time we apply an input of x1 and x2, we should get an output of y1 and y2. So what I mean by that is if our general input x is Vm cosine omega t plus theta v plus j Vm sine omega t plus theta v, or Vm e to the j omega t plus theta v, our output y should be, excuse me, Im cosine omega t plus theta I plus j Im sine omega t plus theta I. What's really interesting about this, and is exactly why we were able to do that complex math earlier that shortened the time that required to do the analysis, is that the real part of the output signal, Im cosine omega t plus theta I, is due only to the real portion of the input signal. All right, so we didn't get quite as far as I had hoped to today. That'll be totally okay though. What we're going to kick things off on Monday is what's called frequency domain circuit analysis. And so what we're going to do in frequency domain circuit analysis is analyze circuits using frequency domain relationships. So just relationships based on complex numbers, and find that we can absolutely avoid all of that terrifying trig and calculus that we did earlier. Working in the frequency domain turns all of our calculus into algebra, excuse me, and we'll see that we can actually treat all of these sinusoidally excited circuits like DC circuits in the frequency domain. So that's enough out of me for today. I hope you all have a safe and pleasant weekend. And I'll stick around on Zoom for a couple of minutes if you guys have any questions, but otherwise you guys head out. Have a great evening.